Okay, so we should be recorded. So again, welcome to RBR. This webinar is going to be about the RBRcoda T.ODO. This is an assessment of the performance for some in long-term deployments and in profiling for an experiment we did a couple years ago in Bedford Basin, Canada. I'm your host, Eric Siegel. I'm a physical oceanographer and the director of sales at RBR. Co-authors on this are Ray Zhang, Mark Halverson, John Taylor, and Greg Johnson. Ray just had a baby a couple days ago, so he's probably taking the day off to have some time with his baby. But John Taylor is a sensor engineer. He has helped design this oxygen sensor, and Greg Johnson is the president of RBR. He's also had a large hand in designing it, and they'll be available to answer your questions, as well as John's going to give an overview of the technology during this presentation. So let's start off by giving you the introduction here. We'll tell you about the CODA T.ODO. We'll speak a little bit about the sensor technology. We'll show you some data from the field, both moored measurements and profiling measurements, a little bit of how customers are using this sensor in different applications, and then of course we'll be able to answer your questions. So here's the sensor. We call it the CODA T.ODO, and T references that it's a temperature sensor, and ODO references that it's an optical dissolved oxygen sensor. If you look at the sensor itself, it has some connectors on the back. It's made out of titanium, and on the front it has the optical foil and the thermistor here. So we're providing about the same accuracy and stability as the Andra optode because we're actually using the same optical foil for most of our products. So in terms of foil stability, dependability, and what you can rely on, we're using that same technology that Andra is using. We also provide a very, very high temperature accuracy where it's calibrated to the same accuracy as all of our other RBR products, which is 0.002 degrees Celsius. So you're getting a very high oceanographic quality temperature measurement in addition to your optical oxygen measurements. It's running at very low power, only 36 millijoules per sample, which is only about 25% of a standard optode. And the whole system is titanium and rated down to 6,000 meters. We have 3 different flavors of this sensor, and each one has a different foil technology and therefore a different time constant. We make what we call the RBRcoda T.ODO Fast, which has a 1 second time constant, and that's typically used for vertical profiling. We make the standard, which is an 8-second response, and we have a slow one, which has a slower response, typically used for moored measurements, but there's a cover over the foil that protects the foil and allows it to be wiped. So you'll wipe biofouling off that, and we'll speak about that towards the end of the presentation. In terms of the interface, it's a serial interface using RS-232 protocol that can be pulled or it can stream the data continuously. And the output parameters that we provide are temperature in Celsius, dissolved oxygen concentration, also another parameter of concentration that's salinity compensated. If you have the CTD, we're pulling salinity from the CTD. If you don't have a CTD, you can input a fixed salinity. We're measuring, of course, and providing saturation and oxygen phase. We've created this as a logger as well. So it's the same sensing element at the top, and we call it the RBR Duet, which means it's a 2-channel logger, which is temperature and oxygen, of course. We're using the same sensing technology, so it has all of the same parameters. We make it in a plastic version rated to 1,000 meters and in a titanium unit rated to 6,000 meters. Again, this can be a slow sensor, so you can put a wiper on it, and it can be configured such that it will run for 2.5 years, making an oxygen and temperature measurement every 10 minutes. So it's very, very low power. It's quite small, and it will run for 2.5 years at that 10-minute measurement interval. Okay, I'm going to turn this over to John now. John Taylor is a sensor technology fellow that helped put this together. So let me see if I can get him on the video here. John, make sure you're unmuted.
All right, I'm here, Eric. If you want to move to the next slide.
Okay. Can you get your video running?
Yeah, no problem. There you go.
Okay.
All right, so I decided I would start with not just the technology behind the RBRcoda T.ODO, but the principle of measurement employed in all optodes. And this is the luminescence quenching reaction by molecular oxygen. So the main element in the sensor is a luminophore, shown here in, oh, sorry, one moment, let me turn on my pencil. And there. Shown here in red, which is embedded in a plastic foil or bonded directly to the glass face of the sensor. So the sensor then sends a pulse of light to the luminophore, which transfers the luminophore into this excited state, and at which point the luminophore then emits light back to the photodetector. Now, when oxygen is present in the environment, it collides with the luminophore, and the energy from the luminophore in its excited state transfers to the oxygen molecule, and the luminophore returns to its original non-light emitting state. The sensor then measures the rate at which this illumination is quenched, and that is proportional to the amount of oxygen in the environment. Next slide, Eric. So there are two main luminophores used by foil manufacturers. The first is the ruthenium-2 complex, which comes from OSFM and is used in our fast ODO sensor. And the second is the platinum octyl ethyl perforin, which is used by Presense, and is present in our regular and slow sensors. These molecules have slightly different emission wavelengths, which require some changes to the optics to accommodate either one. Next slide, Eric. So the fundamental difference between the three foils, which gives them their different time response, is not necessarily the molecule in the foil, but actually how thick the layer of luminophores is on the foil, and if there are other barriers between the luminophore and the environment. So the fast one shown here, it has a very thin layer of the luminophore on this plastic backing, and it gives it the foil kind of a reddish transparent look. Whereas the regular is this a thicker opaque matrix, which is not transparent, and the slow is essentially the standard with an additional layer of protection on top of it, which blocks the outside light, but it also allows for the use of a wiper to clear any growth from the face of the sensor. And this data I have shown here, let me just get rid of my pencil marks. This data I have here shows a simple step response, and where we move the sensor from one solution to another. And you can see the fast in yellow reaches 63% in approximately 1 second, with the regular taking a few seconds longer, and then the slow even longer. But eventually they all arise at the same value. Next slide, please, Eric. So we calibrate all varieties of sensors in the same manner, where we first calibrate the thermistor on the sensor, as we do with all our marine thermistors across a range from -5 to 35 degrees Celsius, all to an accuracy of 0.002 degrees Celsius. We then calibrate the oxygen side of the sensor across 7 temperature ranges, ranging from 1.5 degrees Celsius to 30 degrees Celsius. And at each temperature point, we calibrate it at 7 different levels of oxygen saturation. This creates a 7x7 matrix of 49 points to fit our polynomial, our calibration model. And the residuals must be within 4 micromole for us for it to pass our calibration. Next slide, Eric. So we have also implemented a customer calibration routine in Ruskin to do a linear and offset slope correction on top of the calibration polynomial to correct for any drift to the sensor. This is performed, so to perform this calibration, the sensor is placed into a 0 solution, which is prepared using sodium sulfite, and a 100% solution, which is prepared by simply bubbling air into a bath of water. And the calibration routine is performed on the RSK file, where you use this annotation feature. So when you select this button, you can choose the calibration, and then you highlight the region of your data set that shows those 2 different points. You can have Ruskin identify plateaus automatically, or you can select them manually. Once the plateaus are set, you can enter your reference values, and new coefficients will be generated in the analysis tab above up here. Now, if the logger is connected to Ruskin, you can simply click the Save button, and the new coefficients will be stored directly into the instrument, as well as reprocessing this RSK file with these new coefficients. Next slide, Eric. So the full processing pipeline of the ODO sensor goes beyond applying just the polynomial calibration model and the linear adjustment, and it's depicted here in this block diagram. So the raw measurement is essentially this phase value here, and that in conjunction with the foil temperature, we produce the concentration of O2 using the calibration polynomial. Now, to produce the compensated concentration that one would see in their data set, we have to take into account the effect of pressure on the flux of oxygen into the foil, which is characterized using this simple linear relationship here. And we have to take into account the effect of salinity on the solubility of oxygen in the environment. And that's done using the relationship developed by Garcia and Gordon, using the solubility in conjunction with a few other environmental parameters. We can also produce oxygen saturation. And there you have it. That's a shallow dive into the technology of the optodes and how the RBRcoda ODO works. Back over to you, Eric.
Okay, thanks, John. Appreciate it. Let me put my image back here for the, oops, for the video. Okay, thanks, John. Appreciate that. I'm sure the audience did as well. Okay, let's look at the field validations. Oh, John, if you can clear your artistry, that would be awesome. So we did some experiments in 2018 in Bedford Basin in Nova Scotia. So Bedford Basin is located, or Nova Scotia is located here on the map in eastern Canada, and Bedford Basin is a very large natural harbor directly connected to the ocean. And we chose Bedford Basin as an area because, one, it's close to where DFO, Department of Fisheries and Oceans, and Dalhousie does some experiments, but it's also a very good experimental area. You can see from some data collected years before, published in George et al., that there's a lot of oxygen variability. There's seasonal variability, there's variability driven by physics and by biology, and we can get some very high oxygen concentrations and some very low oxygen concentrations. The deepest part of Bedford Basin is about 60 meters deep, and it's directly connected through this narrow channel to the open Atlantic Ocean. We put a buoy down in the middle of Bedford Basin at a place called Compass Buoy Station, and we were looking at the changes in oxygen over time. So this buoy was developed in collaboration between Dalhousie University and the Department of Fisheries and Oceans Bedford Institute of Oceanography, and it was deployed near the bottom, as I said, in about 60 meters of water. And you can see on it, we have an RBRcoda T.ODO slow here. There's a Seabird CTD, which you can see just out of the picture here. There's a Pro-Oceanus PCO2 sensor. There's a Wet Labs fluorometer, and there's a Suna nitrate sensor in addition. All these data were collected on a Storex logger. The CODA T.ODO slow has a 30-second time constant, as we spoke about. It was deployed between September and December 2018. And the sensor was configured to measure at 1 hertz for the first minute of every hour. And then a couple months later in October, on October 24th, RBR showed up and joined one of the cruises that DFO runs. So they maintain a Bedford Basin monitoring program, which goes out weekly on Bedford Basin and does a bunch of CTD casts. And one of the casts is directly over the mooring location. So we joined them on October 24th, and on this cruise, we put an RBR CTD with 2 CODA T.ODO oxygen sensors. One was the standard with an 8-second time constant, and the other was the fast with the 1-second time constant. Also on this CTD was a Seabird 25 CTD with the Seabird 43 oxygen sensor and water bottles. So we'll look at the data comparison for vertical profiling with the RBR oxygen sensors against the seabird oxygen sensor. And for long-term deployment, we'll look at the water bottles collected against what we're measuring on the bottom mooring. So as you can imagine, we deployed the equipment in September 2018, and every week DFO goes over and does a measurement of water samples near the bottom. But in October, we went as well. We dropped the CTD with the oxygen sensor and water bottle down to the location of the mooring. We collected data there on October 24th. So as I said, we'll be looking at data that's both time series as well as a profile. So let's start with looking at the mooring data. This is a measurement of temperature collected from late August till mid-December 2018. And what we see here in red is the temperature measurement from the CODA T.ODO on the bottom mooring. What you can also see, just barely, is the blue measurement, which is the temperature sensor from the seabird that was also on the mooring over time. So you can see that the temperature data fall right on top of each other, and they both show really nice temperature measurements, getting as cold as about 3.5 degrees and as warm as about 6 degrees Celsius. If we actually do a measurement to compare the difference, you can see a nice tight histogram. The mean difference is 0.004 degrees Celsius, which is within the accuracy spec of plus or minus 0.002 for both the RBR and the seabird. So we have good performance in temperature from both units. And now we'll look at oxygen. So the only oxygen measurement on the buoy, on the subsurface buoy, was the RBR T.ODO. And that's in this red and orange line here. But then you should remember that weekly, the ship went over and sent the CTD down that had a Seabird 43 oxygen sensor, which are the triangles. And they took water bottle samples, which are the black dots. So we have weekly measurements to compare against. And when we look at that, we can see that when we compare the RBR oxygen sensor against the water bottles, we have a mean difference of minus 0.36 milliliters per liter. And that's a little bit higher than what we would expect for the accuracy performance of the RBR. But then when we look a little closer, we see that two things are true. One is that the seabird, which is the triangles, is also always lower or biased low compared to the water bottles in the same way that the RBR is. And we see that before this large mixing event, and then after the mixing event, we see that everything is more aligned. And so what we're expecting here is that there's a bit of vertical stratification where the oxygen level is a little bit lower, deeper down where the RBR is located, and even where the seabird is located on the rosette compared to the water bottles, so that both the seabird and RBR are showing lower values than the water bottles before the mixing event. And then after the mixing event, everything is lined up well. And when we do the difference measurement between the RBR and seabird and between RBR and the water bottles before the event, we see there's a larger difference, and after event, it's a tighter fit. Now we're going to move into vertical profiling. So there are three lines that you'll see here. There's the Seabird 43 line from the surface down to about 70 meters. And that's a black line that we see here. This is from one vertical profile where the oxygen level goes from about 2 milliliters per liter up to about 6 milliliters per liter. And then directly traced on top of it is the RBR fast oxygen sensor. And we would expect that it would have the same performance, and it shows very good performance. The blue line here, which is a little bit smoother and lags the other one going down, is the RBR standard oxygen sensor. This is one with the 8-second time response, and therefore we would expect that there would be a little less resolution in detail and a little bit of a time lag when we go through different changes. So that's about what we would expect. And when we look at the difference in measurements between the fast RBR and the seabird, we see that there is very, very good agreement centered on zero difference and very tight. And as expected, we would see very accurate in terms of the mean measurement for the standard, which is the 8-second time constant, but spread out over a little bit wider histogram. Now, interestingly, we know that a lot of people have oxygen sensors that have an 8-second response time. It could be profiling with an Andra, it could be profiling with the standard RBR with an 8-second time constant. And so we started looking at how could we correct the 8-second time constant sensor to better fit what is the fast sensor. So what we have here is the fast data, as you would expect, which is in black. We have the blue data, which is the same as what you'd saw before, the raw 8-second time constant sensor. And then we've gone through and done a correction algorithm or a tightening algorithm that will simulate a faster response. And that's what we have for the corrected yellow here, which means we're able to correct the 8-second time constant sensor to provide a little bit better simulated resolution. And when we look in terms of the histogram here, we can see that doing the correction tightens everything up. And we talk about this correction in a paper that we wrote that's on the RBR website, looking at Bedford Basin data. So you can review a bit more there. Should also say that this correction is available for free in the RBR-RSK tools toolbox, which is a free MATLAB toolbox for post-processing your data, where you get to apply this correction in that toolbox. So in summary, we can see that the T.ODO slow provides very nice measurements and very high stability for long-term mooring applications. The T.ODO fast provides very high accuracy and high time response for vertical profiling. And the standard does have the time lag that one would expect, but it can be improved with post-processing. We'd like to thank the folks at Dalhousie University and the Coastal Environmental Observation Technology and Research Group, led by Richard Davis, and folks at Bedford Institute of Oceanography that helped to provide all of the support for this in terms of the ship time, some data analysis, the moorings, and all the ancillary equipment. So thanks to those folks as well. Let's look a little bit about applications, how people are using these sensors in both fast, standard, and slow variants. So as you can imagine, people are using the fast one mostly for vertical profiling, the standard for a variety of vehicles and floats, and the slow for a variety of mooring, both inline moorings and on the bottom moorings. So let's look a little bit more. Here you can see a very standard application for vertical profiling is connected to an RBR-CTD. Here we have the oxygen sensor and a turbidity sensor connected to an RBR-CTD for vertical profiling. This is a nice photo of the RBR oxygen sensor connected to a Maestro CTD that also has, we can see at the bottom, turbidity, pH, and a PAR sensor. And this is a photo from the Nature Trust of British Columbia, where they're doing some estuary measurements. For vehicles and floats, we're seeing the oxygen sensor being used on Argo profilers along with the RBR-CTD. Here's the CODA T.ODO oxygen sensor. This is on the MRV Alto profiling float. And what's really cool about this is that this is an unpumped oxygen sensor where the oxygen measurement isn't in the plumbed system, which means when the float comes to the surface and the antennas at the surface sending data through satellite, the oxygen sensor is in the air. And that means that we can make 100% oxygen saturation measurement, and that can be used to constrain drift in an oxygen sensor over very long-term deployments, especially when you're not going to get the sensor back, like for an Argo float. Oxygen sensors are also being used on gliders because it's a very low power oxygen sensor, and on gliders we know power is a limiting factor in so many ways. It's a really good choice for making an oxygen sensor, an oxygen measurement. The CODA T.ODO can be integrated directly into the glider infrastructure, or it can be connected to an RBR Legato CTD, which is then connected into the glider. And that's what we can see here is the oxygen sensor and the RBR Legato CTD. And we can see some nice measurements. This is done in a polar area where the water is quite cold, down to 3 degrees Celsius. And we have low oxygen concentration at the bottom, high above. This is about 100 profiles down to 1,000 meters, pretty standard glider operation. The CODA T.ODO is also included in the Saildrone CTD. So Saildrone and RBR partnered together to develop a customized CTD package that fits within the sail drone sensor bay. And that includes the standard RBR temperature and conductivity cell. But you can see embedded in this is the RBRcoda T.ODO oxygen sensor. And finally, for moorings where we expect biofouling, obviously deep water moorings that are below the photic zone will be clear and probably not have much biofouling. But in areas where there will be biofouling, we can install it with a ZebraTech hydro wiper. So this is a system that goes back and forth over the optical lens and keeps it clean. This photo here is a great photo from the UC Davis Tahoe Environmental Research Center. You can actually see the wiper here fully covered in slime from being deployed for a long time. And it wipes over, but you can see how clear the face is. And this is what the hydro wiper would look like on another integration for the T.ODO, where the wiper will go back and forth across the face at the frequency that you set it up. And I have a note here that says it can be set up to wipe every 2 hours for 1 year or every 4 hours for 2-year deployment. So there's lots of batteries and very low power for long-term deployments. So that concludes this presentation. We thank you for joining. I'm going to quickly tell you what's coming up next in the next few weeks, and then we'll open it up to questions. I can see lots of good questions have been asked on the chat area. So starting next week, we'll have a presentation about the DMO wire walker and how it's used for vertical profiling powered by the waves. Following that, we'll be speaking about the Ruskin mobile app and how you can use your tablet or your phone and Wi-Fi, as well as built-in GPS to map your cruise and see your data. Following that, we'll have some presentations about dynamic performance through gradients and long-term stability of the RBR sensors. Following that, moving into late May, we'll have some presentations about new technologies for making measurements. One is the RBR Legato CTD on gliders, and the other is a fast biophysical underway profiler called the ECO CTD. And finally, as I mentioned, Ray had a baby last week. Finally, in June, we think he'll have had enough sleep and maybe enough coffee to give a nice presentation about the toolbox we talked about, the RSK tools, which is the free toolbox to make CTD post-processing and data visualization efforts. Okay, so thank you very much for joining. We're going to now open up to questions. I'm gonna see if Greg's available to let me know what kinds of questions he's been fielding and which we should open it up to in terms of reading off important questions and then opening it to the rest of the group.
Hi, Eric. It's not just me, but John's been on as well. John, I think you've answered many of them. There's maybe one at the end, which is about UV anti-fouling control. This is from Kristen. UV is not a great one to shine on the foil because it bleaches it and ages it. And it's actually one of the processes we use to bleach, to pre-age the foils before we ship them. It gets them out of a kind of polynomial or an exponential power law drift curve into a nice linear section that can be easily corrected. So UV is the enemy of a luminescent foil. If you want to use UV, you would need to use that being said, UV is most commonly used as an antifoulant on long-term moorings, and long-term moorings don't need the fast time constant. Because they don't need a fast time constant, therefore you can use the 30-second foil. And as Eric showed at the beginning, that 30-second foil has a Teflon membrane over the top, which protects the foil itself. Use in sunlight, for instance, and I believe somebody earlier, was it Tom or Sean, was asking about use on the floats. You want to make sure that you use the right foil for the length of deployment that you're going to be looking for. Dasha Atamanchuk is on the call as well, I think, and she's got a lot of experience using the both the slow foil from Andhra and the normal speed one. We use the same foils there, and we'll be able to comment perhaps on long-term deployments like AMOC or OSNAP.
Okay, Greg, thank you. Are there other questions that were asked above, even if they're answered, might be useful to log in the video or for people that haven't been following the text chat?
Well, it's been quite busy, let's say. So there were some questions about battery life at the beginning. Oh, does the RBR duet record internally? Yes, it does. Can the sensor be integrated to any third-party data logger? Yes, so the CODA T.ODO has serial output, and that can go to any instrument that's got serial input. In the duet T.ODO, which is recording internally, it can record on a single AA battery for about 2.5 years at 10-minute sampling period. The internal memory, somebody asked about, it's not actually too important for the duet T.ODO because it is limited by the battery life of that optical sensor. However, if we make the same instrument measuring just temperature, and just to give you an idea of the amount of memory it has, it can record 25 million readings on a single battery. So the Solo T that measures just temperature can do that. Let's see. It was a 1 Hertz sampling rate in the response figure. That's correct. The fit that was shown was the combined fit from Garcia Garden. There was a question about the where do we get the reference phase from in our calculations, and those come from a parallel LED. So we use 2 LEDs that are from the same batch in semiconductor manufacturing. That means they age at the same way. One of them sees the foil and one of them doesn't, and we measure both of them simultaneously, or for each measurement we measure one then the other. There was a question about reprocessing data sets with calibration coefficients that you obtain after a deployment, which is entirely possible. And I think I'm scanning down to the end. Oh, and how many batteries needed? So if you're using the CODA T.ODO, which is the sensor that Eric displayed at the beginning that's standalone, then you just need a 12-volt source to power it up, and it will spit out data on the serial lines. If you're using the duet T.ODO, which was the instrument with a yellow housing, that uses a single AA battery of any variety, really, and can do that. You can also have the T.ODO sensor added to any of our CTDs, in which case the CTD itself supplies the power, and that just uses 8 AA's. Eric, back over to you.
Thank you, Greg. I want to open it up to anyone else that's on the call that hasn't written in their question but wanted to unmute themselves. Let's see if we happen to do it randomly in an orderly fashion. You should be able to unmute yourself. George, I see you're unmuted at the moment, or maybe it's just you're on a telephone. Is there anyone that would like to ask a direct question? Okay, at the moment, I've just seen one new question come in by text, which is from Julia. Hi, Julia, good to hear from you again. What's the upper limit of the ODO in terms of saturation? I'm gonna take a stab and say we calibrate to 120%, but Greg or John might be able to correct me here.
That will have to be John, but I'm not sure that I have a feeling he might.
That is correct, Eric. Yeah, 120%. And so in 5 degree water, or 1.5 degree water, that works out to, I think it's close to 600 micromole is the upper range in that sample.
Okay, are any other questions that come through by chat or verbally? Okay, I think we want to thank everyone for joining us for this call and invite you to come back next week for the DMO Wirewalker RBR presentation, which should be quite interesting as well. Okay, thanks everyone. Thanks very much. See you next week.
Bye everyone.
Thank you.